Thank you very much for invitation. So today I'm going to speak about famous results in behavioral games and economics in general. It is either called ultimatum game or ultimatum bargaining. It is pretty much the same. I will. I have done this work with my colleagues Armen, Allahverdyan, and Lida, Aleksanyan. We have a published paper. I will. Generally, I'm going to speak about the results in this paper, but I will start with something that I'm sure most of you know what is it about. Maybe, but for keeping things linear, I will try to go through that through expected utility theory, through lotteries, and so on, until we have the tool of regret, and then I will apply this regret tool to the ultimatum game and show the predictions how regret theory is applied and how it predicts the behavior, which is in line with the results already known. So first of all, it started when we were working on the famous paradox by Maurice Allais. We were trying to understand behavior, but without cutting off all the axioms. Like the prospect theory doesn't cut out all the axioms, but it cut out some. We were trying to find another tool which will maintain the several axioms of expected utility and try to apply them to understand how they will predict the behavior in Allais paradox, and then we'll try to apply to something else. Let's speak about the general decision-making problem. I will go fast through it because I know all of you know what is going on. So we are facing the choice of two lotteries. These are generally, and within the expected utility theory as well, these are discrete random variables with some known distributions, and we are if we interpret x's and y's as amount of money or something else which can be given value to utility, we are faced with the choice between these two lotteries, these two random variables. So what is going on? We are going to, the main theory started with some axioms, some rules, which can be applied to choose between these lotteries. And there were some rules which were thought to be indispensable in these cases. So you can they are required in most of the settings. The completeness, which is about that you can compare any two lotteries, transitivity, continuity of the rule, and the stochastic dominance criterion, meaning that if one lottery is stochastically dominant, if one random variable is stochastically dominant over the second one, the first one should be chosen. So the expected utility theory was talking about the existence of this utility function, and you can calculate the utilities of these outcomes and compare the average, the mean utility within the first lottery to the mean utility of the second lottery. This is a general setting. However, this theory generally by von Neumann and Morgenstern was that the existence of this utility function within the framework of several axioms was proved by von Neumann and Morgenstern, but these had some drawbacks which were found when Maurice. Generally, it was known that it has some drawbacks, but the general drawback was shown by the example of which was concocted by Maurice Allais. What was it about? It was about four lotteries divided in two groups, and the example which I can show, if we agree to see, but I didn't want to elaborate much about that. But in any case, okay, let's go to the end. So what was the Allais paradox? There were four lotteries.
Vardan, take as much time in the beginning to explain the main concept, because I'm not sure that everyone here is familiar, so feel free
I'm
to
sorry, I'm
no,
sorry.
no, no, no. I mean,
Uh,
you are doing it perfectly well, but feel free to continue like this. Don't run.
okay, okay.
Thank you.
So for a moment, let's talk on the expected utility theory, which says that you can have this utility function. You can calculate the average utility of not average amount of money what you get, but average utility. So average value for yourself, a level of satisfaction of yourself for yourself within the lottery. So each lottery has its expected utility. And you choose one lottery over the other when the expected utility of this lottery is higher. But so you calculate these average utilities and you are fine with that. This has some prediction of general behavior. But in extreme cases, which was shown by Maurice Ale, this is violated. So here was his example in millions. So there are two stages of when in each stage decision maker faces choice between two lotteries. The first one here is you get $1 million with probability 1, so for sure you get $1 million. And the second lottery is that there is a small chance of 1% that you will not get anything. 89% with 89% probability you get the same $1 million, and there is 0, 1 or 10% probability that you will get $5 million. And the second pair, which here is the third and fourth lotteries, the second pair, you are either taking this lottery when you have 11% probability that you will get $1 million and a huge probability of 0.89 that you will get nothing, versus the fourth lottery, which is where you have this 0.9 probability of getting nothing, but you have 10 probability of getting $5 million. And it was tested several times. Then the prediction is that most people in this setting, they choose the fourth lottery. Between the third and fourth one, they choose the fourth because the general explanation is that the probability isn't that much different of getting nothing, but when we are getting some amount of money, it is 5 times higher than in the case of the third lottery. So most of the people chooses the fourth lottery. In the first couple, the decision makers mainly choose the sure $1 million versus the case where you have probability of getting nothing, even when you have this probability of getting $5 million. So what was this paradox showing? That if you are using expected utility theory, you cannot explain this behavior. So you cannot explain the behavior when one chooses 1 over 2, but chooses 4 over 3. With that, there is no utility function. It has nothing to do with risk aversion or risk loving. There is no utility function where you can apply this utility function and get the situation where the expected utility of first lottery is higher than than of the second one, and the fourth one is higher than of the third one, without regard of risk attitude. So, and this generally showed that the expected utility may be not the main tool which is used, or it is used in not all situations. It is also known that the reason why why expected utility fails to explain the behavioral decision makers in this paradox was that the fourth axiom, it is called the axiom of independence, or in some cases this is called independence of the relevant alternatives. In game theory, it is known in this name. So there is an axiom which was violated in this example by decision makers, it is seen as the most controversial of these axioms. And there were proposed on this ground, there were proposed several new theories, and the most famous one is the prospect theory by Kahneman and Tversky. But this was much more behavioral in a sense that this behavior was tested statistically and found that when we are talking about losses, people behave differently. When we are talking about gains, people behave differently. They have different attitudes based on their starting points and so on. But the theory, the prospect theory, was reevaluating the given probabilities. So it shows that in general, decision makers either do not believe the given probabilities or have inclination to change either pessimistically or optimistically so they can believe that there is higher probability that you can gain nothing or smaller probability that you will gain $5 million in this case. So let me go back to these axioms. I'm sorry to do this way. So these were the four main axioms: the completeness, the transitivity, and continuity. Continuity is about continuity of utility, not continuity of utility function, the continuity of decision rule itself. So it is continuity in probabilities. It doesn't require even continuity in utility function, but general theory requires it. So we'll stick to it. So these four axioms, and the fourth one was the most controversial one, and it is known that this axiom is really violated in the Aller paradox. So the main theories were alternatives of expected utility theory, which arose at that time, were prospect theory, which later were have extension generalization to cumulative prospect theory. This is not really generalization because prospect theory is known to be non-transitive, so it violates also transitivity axiom. The cumulative prospect theory overcome that problem, made it transitive, the decision rule transitive. There was rank-dependent utility theory, which was by Quiggin. This is generally the discrete version of cumulative prospect theory, though it should be stated that this came before the cumulative prospect theory himself. But there was another tool, which was called regret theory. And I will explain in a few seconds what is regret theory. So regret theory was proposed by several authors. It is believed to be done independently because it was on average in the same period of time. The main authors, the main people who is attributed to regret theory are Bell and Lunz and Sugden. So what is regret? Regret is a functional on the difference of utilities. So let me just explain what regret can be, how can be formulated. So suppose we are facing the choice between two lotteries, and we are looking, for example, the following case. If I chose the first lottery, how much will I regret for not choosing the second one? So it is compared pairwise. So if the outcome of the first lottery is X1, and the outcome on the second lottery will be Y1, I will regret the difference of utilities. I will regret utility of Y1 minus the utility of X1. So in average, I will regret this much. So the probability that the if outcome was on the first lottery and the just outcome was on the second lottery times how much I will regret. So this is the average regret when I have chosen the first lottery, but I haven't chosen the second. So this is the one-way regret. But it is incomplete in a sense that you should also compare it to the case where you have chosen the second lottery and regret for not choosing the first one. And this is another form. So this is the analog of it for that case, when I have chosen the second lottery and I regret for not choosing the first one. And their difference is called a regret function or regret functional in general. So these R, which is already unconditional or just can be written by R, it is the regret functional. G is the functional difference between F, this F, and so F of choosing the first lottery and not choosing the second, minus F of choosing the second lottery and not choosing the first. So the order still makes a difference. So if I switch here the indices, I will revert the sign. And the general rule is the following: you choose the first lottery over the second. If choosing first lottery and not choosing the second, you will regret less than choosing second lottery and not choosing the first. So if this difference is negative, you will choose the first lottery because you regretted less for choosing first lottery and not choosing the second over the opposite case. This is the general rule. It was not proposed in this form, but generally it was proposed for independent lotteries. We were trying to generalize it to a more general case where the lotteries can be, for example, correlated. So the outcome of lotteries can, so for example, the one may be compounded by the second or be made of the second plus the third one. So this is the general rule. Of course, G is the odd function. It is because it is x minus f minus x. That's why it is odd. So, but we will still focus on the independent lotteries. So where the distribution here is PYQG. So PYQG. And we were able to show the following properties. The first one is obvious. It shouldn't be named even a theorem. That is an obvious one. So the regret function is continuous in probability. The second one is that regret satisfies the stochastic dominance property, meaning that if the one random variable is stochastically dominant over the second, you will choose the first one. And the third property, which was the crucial one, was that if you want your rule to be transitive, there is only one, up to choice of the parameters, only one function, G function, which is A times sinus hyperbolic some beta parameter x. So instead of x, there should be utilities. It is just the formulation of the function. So generally, these results remained unnoticed. We were able to retrieve it, but it can be said that it was proved. Just they didn't understand that they have proved this result. It was by Fishburne in his famous paper on, not so famous paper on the cases when you choose between lotteries, but you don't have the general expected utility rule. So he showed when the rule can be transitive. We just applied it, and for the regret case, when the regret is based on the difference of utilities, this is the only functional form that satisfies transitivity. It is easy to show. It generally comes from Cauchy functional equation, but with multiplication, not with sum. So for the f functions. So we showed that f functions satisfy the Cauchy inequality in the form that fx plus y is fx times fy, and when we want it to be continuous solution, the only solution is exponential one. So the difference of exponential functions were so it is exponential x with some parameter minus exponential minus x with the same parameter, so it is sine hyperbolic function. So these main results were shown in another paper with my colleague Armen and Allahverdyan. And we were able to predict the behavior in Euler paradox of decision maker with some small addition to this g function. And this addition was that this g function should be superadditive. Whenever it is superadditive, the behavior in Euler paradox is fully explained. But what does superadditivity means in the framework of regret? It says that when you have small regrets in different times, that is amounted to less regret compared if you have these losses simultaneously. So if you lose this too much money at once, it will amount to higher regret, or too much utility, I'm sorry, at once it will amount to higher regret than you will regret for a few amount of money of utility and the other part on the next day, for example. And this property was already known about regrets, maybe not in decision-making theory, but it was a famous property of regret itself, so as an emotion. And if this property is maintained, the behavior of decision makers in Euler paradox is fully explained. So we didn't stop here, and we understood that we can apply this law.
May I ask you a question, Vardan?
Yes,
A
of
matter of
course.
curiosity. Ale was still alive when this result was established?
Yes, I'm sure he was. It was, I don't remember, but it was about, no, our results or results of regret theory itself.
No, the result about regret theory. Your result, you are too young.
Yes. No, the results on regret theory, yes, there were 1980s, 1979, if I'm not
Okay, so he was aware of it. Okay,
Yes,
thank you.
So we tried to apply this regret theory to one of the famous problems, which is called an ultimatum game. It can be treated game theoretically, but the result is not that interesting, and I will talk about it. But it has some economic consequences, and you will see it is also some kind of a bargaining problem, but bargaining problem where each player has a respective role. So in this ultimatum game, you have two players. They are splitting some amount of money. They are dividing between themselves some amount of money, but they have roles. The first one is the proposer. So the first one proposes some split. So he takes, here we have, the small a is the money he gets. It is, let's confine that, let's agree that we are talking about the money, not utility yet. So he will get the, but we can change later if you want. He will get the amount of money A, and the second player will get the remaining. So in general, it is seen that, for example, a close to fair split, which is 50-50, does not take place. But for example, a split like 60-40 is quite widespread. So for example, the first player tries to take in 60% of the main amount of money. The 40% is for the second player. And generally, the second players agree with this split, and the split follows. When they disagree, they take the so-called disagreement money point, the defection point in bargaining theory. So they both get nothing. The problem with this game was that usual game theoretic prediction of behavior of two players were the following. The second player, initially not having any money out of this money A, will accept any offer higher than 0 because it will make his his welfare will increase. Maybe with a small amount of money, but it will increase. And so the first one will be inclined to take, for example, higher than 99% of money to him, because the second player will accept any offer, any non-zero offer. So this was the prediction of game theory, and it was shown that if we are talking about even not so dynamic framework, but even in dynamic framework, this is the subgame perfect Nash equilibrium of the two. So this is the fair. Here I'm talking about the fair split, and what is called fair split. If A is close to A, it is not equal. That is, if it is close to the half of the money, it is called the fair split. So it is a vague concept of fairs. But the behavior is the following. So there are twofold breaking of the predictions. The first one is that the second players are, so the responders are generally inclined to reject unfair offers, where unfair is meaning that that the first one is taking, for example, more than 80% of money to himself, while the other less than 20% is going to the second player. These splits are rejected fairly often. Fairly often they are rejected. And the second in inconsistency. So the second how it's said. So there is another way which the theory doesn't work. It is that the first players, so the proposers, are not generally deviating from fair split too much. So they are not making unfair close to 99% or higher splits. So they don't take 99% for themselves. But the theory was predicting there should be that way. So we were asking ourselves, may this behavior be rational? And we came to some, in our case, more or less rational explanation why this can happen. So if you are using one rule, which I will speak about in a few seconds, then the prediction, the behavior in these games can be predicted pretty well. So, and this is the rule which sounds like this. I will, if I'm the second player, if I'm the responder, I can reject the offer if the utility I lose or the money I lose, whatever you want. So it is about utility in general, but if the utility is linear, you can take it to be money. So the utility I lose, so the regret over the utility I lose is less than the regret of the first player, of the proposer, for not proposing me better split, then my rejection would have the consequences. I may force him to change. For example, if we meet the next time, he will be more inclined. So he lost more, in a sense that he regretted more of his own choices than I regretted. And if we apply this rule, which is fair enough, so this rule, it is in several papers. It is called the rules of war, or for example, in nowadays situation, it is like when you use sanctions, economic sanctions, you are you are expecting this, so you know that you will lose less than the other party. If you are losing more than the other parties, that's not very reasonable to go to this economic sanction. So it is generally called one of the rules of wars. In several papers, in several famous, even non-scientific papers, this is cited through. So we applied this rule to the ultimatum game, but I would rather say to the mini version of ultimatum game when you can't name any A. You are there are only few splits you can offer. The first one is in your favor. The last one is in the favor of the second player. So you here take the least amount of money to yourself, while in the case of A0, you have most amount of money of yourself within the possible splits. And here I have written this, I'm not sure about this sentence. I have written that any discrete game can be modeled via lotteries. This may be not generally true, but in most cases it can. So I will so to apply regret, we should have lotteries, because the regret itself and like an expected utility theory was about comparing lotteries. So to understand what we are comparing, what we are regretting about, we should state explicitly what these lotteries, what form are these lotteries. We should compute the regret of first player, and we should compute the regret of the second player. And to do this, we have the following model. So there are probabilities of accepting the offer, accepting the split. Of course, when the first player is splitting in his favor, so he takes A0 to him and A minus A0 to the second player, the probability of rejecting is high, so the probability of accepting is lower. Whenever you go further and further, you will the last option, which is in favor of the second player, will be accepted because within the initial framework, so when only these split were available, these were the most acceptable one by the second player, so he will not reject that offer in any way. So, but there are probabilities that he will reject the other offers. These probabilities are increasing up to 1 minus P0. So P0 is probability of accept. And there are also this let's call it, I don't know, the pi i's. So when we have where the pi I is the probability of proposing the split, so the is split. So the pi I is about taking the money AI to himself and letting the other one to the second player. So it is a mixed strategy game. So you are playing not only one, you are not proposing only one split, but you are proposing with some probability, using with some mechanical probability tool to generate the probability and give you the opportunity to play one of the splits, so to offer one of the splits. So what lotteries is the first player facing? He faces the following lotteries. He could give the best version to second player, and it would be accepted with the probability 1. But when he plays probabilistically, even non-probabilistically, so it can be pi 0 can be 1, and the other pi's can be 0, so he will have the probability of taking A0 P0 and the probability of getting nothing 1 minus pi P0. So depending on the probabilities he is playing his splits, so he's offering his splits, he is facing these two lotteries. and he chooses these probabilities how to play. But with the fixed probabilities of playing, he may compare the regrets over choosing this lottery versus choosing this lottery. So he faces these two options with the fixed pi probabilities. So what choice is facing the second player? The second player is facing the following choice. He can either always accept as the theory predicts. So whatever he is offered, he takes that. So all p's are 1. He does not going to reject any offer. Or he can sometimes reject the offers, and he will get this amount of monies with these probabilities. Pi n is 1, that's why it is not written here. Or he will get 0 when he rejects, and the probability of getting 0 is 1 minus the sum of the other probability. So these are the extreme points. This point is that the first player is playing along the second player, so in favor of the second player, and this is the case when the second player responding according to the theory to the first player, so in the favor of the first player. So let's compute the regrets of the first player, the second player, and compare them. So this is the general formula. I will not. It is very easy. So it was just we applied this. I'm sorry to go back, but we applied this formula to the lotteries in each case, and here is the regret of the first player, the regret of the second player, and we are just comparing them to each other. So for a given pi probabilities, if there exists the probabilities p, which can force the first player to regret more, then we are saying that the second wins. So if the regret of the first player is higher than the regret of the second player can force by choosing right probabilities. So if there exists some p's for which this is true, he can force the first player to change his own probabilities of playing, like to play in his favor. Otherwise, if there doesn't exist these p probabilities making the R2 less than R1, then the player one we say the player one wins. It means that the second player cannot force the player one to change, to alter his choice, his proposal. So this is the case, and we were able to show the following results. If we have only two possible splits, the fair one, for example, and the unfair, so the unfair one, I'm sorry, and the fair one, for example. If only these two options, it is called mini ultimatum game, when you have only two options to propose, the greedy one to yourself and the fair one. In that case, if there are only these two options, and the second one is also the better for the second player split is also greedy in some sense, so it is then higher than 50% of the money, then second player can always win over the first one. And if if the case is that A1 and A0 are such that A0 plus A1 is less than the money itself, the whole money itself, then second player can never force the first one to play. So the first one can choose the right probabilities, and the second player cannot force him to win. But there are still situations when the A0 plus A1 is higher than IA, the big A, and second can still not force the first one. So suppose that the first split is 80-20, and the second split is, for example, 55-45, then the second player can force. If the second split is like, for example, 30 to himself, to the first player, and the 70% to the second player, so it is generous one. But still 80 plus 30 is higher than A. But with the right probabilities of playing this, of making these offers, the first one can have this advantage in the sense that the second one cannot force him to play, to solely play the more generous option. So if there is 50-50 and 80-20, for example, only these two splits, the second one can generally force the first player to make the pair split. While if this is somewhat smaller than 50, the first player can while wisely choosing the probabilities can win over the second player. So and we were able to, I will just say what we were able to explain from experiments. The first one is the rejection of unfair offers. Our theory predicts this behavior pretty well up to the values of experimental results of how much % of people reject that offer. There is another phenomenon called super fair phenomenon, which is an interesting one, and we still don't understand the result itself. But so when there are situations when in mini ultimatum game there is fair option, so 50-50, I can split, if I'm the proposer, I can split this money 50-50. And there is another option of super fair split when it means that I'm too generous. I can take 40% of money to myself and give 60% of money to the proposer. And sometimes, we don't understand why, but sometimes people choose the second option. The proposer, the decision maker, choose the second option. So they choose the more generous option. And this is called super fair phenomenon. And the problem is that this super fair option being chosen is sometimes rejected by the responders. So the generous options are rejected. So the one explanation is that people demand fairness also for themselves. So they will say that, no, it's unfair that you give me more money than you take it to yourself. So we were able to capture this behavior as well. We were able to capture the rejection. So we were able to find that there is a situation when there it is rejected. We were able to find the explanation why they sometimes, not always, but sometimes are more generous than fair. So this they proposes more than 50% to the responders. Also, we were able to recover the results that the rejection rate decreases when the A amount of money which we are speaking about gets nominally high. So, for example, whenever we are speaking about $1,000, it is one story. When we are talking about $1 million, it is another story. And the rejection rate is much less when we are talking about $1 million, and you are, for example, proposed 20% of this money. And this behavior we were also able to explain this behavior in our theory, within our theory. And there were one thing which was not tested generally, and where we deviate from the fairness paradigm, so explanation without regret explanation. So it is the following, that the richer agent, if he truly takes this fairness norm, he will if the fairness norm is applied to the whole utility, not only the part of the gained utility throughout this game, he will make more generous offers to the agents, to the responders who are poorer than themselves. the fairness prediction is that richer will make more generous offer. And the second part of it also says that if the richer is the responder, he will agree to take less amount of money. So the richer agent gets less. This is the fairness prediction. Our prediction is that richer agent gets more because he can tolerate more regret. He can tolerate more losses than the other agent may tolerate, the poor agent may tolerate. So he will push the poor agent when, for example, he is a responder, he can push the poor agent to make more generous offers to him. So these, and we are ready to see any experimental results. So why I'm unsure, I said that I'm unsure that this explain all the behaviors, because this was not tested. Maybe fairness theory is rich in that aspect, so we can predict this behaviorally. The final notes is that regret was proved to be a very powerful tool, and that it possibly can explain the most outcomes in ultimatum game behavior. And this is the paper which was published in Journal of Economic Behavior and Organization this year. So thank you, and this is thank you in Armenian.